Recorder is on. All right. So let me. Okay, we still have a little bit of time. We are getting there. All right, it is 9 o'clock. I'm going to get started. So what we'll do today is to look into how to return a value. But I did give you guys an assignment on the other day. It was not supposed to be graded, but it was some activity for you guys to do. So I'm combining that with something that I'm doing today. So I'm not going to give you the quote unquote solution for the other day, but I will give you some additional stuff today that will also answer the question or the ungraded assignment from Tuesday. So if you have kind of worked on that one quite a bit, you would also be able to understand what we are going to talk about today. So let's go ahead and get started. So for this class, I have not included the new module that I wrote. So let me do that first. This is the problem of teaching two different classes because um, when I do changes, make changes to one class, I have to manually put all those changes to my other class, which is not a big deal. I just have to kind of do that first. All right, so the new module is, we have this already. It's just that this one is I think it's a better summary. So let me put it into our module first for this class, and then we'll go ahead and proceed with it. So I'm just adding a external URL to this particular module, which has to do with the TTP caller callee agreement / contract. And add item. It'll be added to the bottom, unfortunately, and then I have to move it back to where it is supposed to go. All right, so we're getting there. Okay, one more, I think. There we go. And I'll unhide it so that this way you guys can get to it too. So this is the old version. This is quote unquote the new version. They contain kind of the same information. So let me just kind of go there first. Um, so this is the caller callee agreement, which is basically stating what the caller is what is assumed to be the responsibilities of the caller when you're calling a subroutine. And then on the flip side, we have the responsibility of the callee, which is down here. So we'll start with the caller. We haven't really talked about arguments yet, so we can kind of ignore everything that has to do with arguments. So we can, for now, kind of ignore this portion, okay, because we have not talked about arguments yet. On the other hand, we have talked about the return address. So this is important, okay? The return address, which is the address of the instruction right after the jump to the callee, is pushed after all the arguments, if there are any arguments. So since we are not going to use arguments for now, this is the only thing the caller has to push on the stack. And then after that, we jump to the entry point of the callee, which is typically a label that is named after the name of the function that we are trying to implement. And then the callee should return to the instruction that is right after the jump instruction. This is the bullet point. If the callee returns a scalar, which is what we're going to do today, is to handle a return value. So if the callee returns a scalar value, the return value is assumed to be in register A. So that's an assumption, okay? We have to pick a register out of the 4 registers to contain the return value. And just by convention, I have chosen to use register A in this case, just like I chose register D to be the stack pointer. All right, so there's nothing inherent to the instruction set nor the registers that I have to choose register A. I just have to choose one particular register, and I said, let's pick register A. A for answer. How about that? Okay, so there's our reason to use register A. Coincidentally, if you use the x86 architecture, it is also returned in the quote-unquote register A, which is known as AX in 16-bit mode, EAX in 32-bit mode, and I think it's HAX in 64-bit mode. So that's kind of interesting, coincidental. The values of registers A, B, and C are not assumed preserved by the callee. So that means if the caller has figured out something important, put it into register B, and then proceed to call a subroutine or to call a function, well, do not assume that register B will retain its value. Is that okay? This is a really, really important concept because you want to make sure that none of the registers from the caller's perspective is holding anything important. Okay, so that's important. And I'm going to have to put my, okay, I'm going to have to reconfigure my do not disturb because I exclude my Ring app simply because at night I want to be alerted if there's something happening. So I'm going to have to get rid of that. All right, so that should not alert me anymore. There we go. All right, so we are not dealing with arguments. So at this point, we don't have to talk about that point. On the other side, on the callee, which is the function being called, on that side, at the entry point of the callee, the stack pointer is assumed to point to the return address. This has to do with the caller is going to push the return address as the last thing that it pushed before jumping into the entry point of the subroutine. So as a result, the subroutine being called can make the assumption that the stack pointer points to the return address at the entry point of the subroutine. Is that okay? Are there any questions? Okay, if there are no questions, we're going to continue. We are not going to talk about arguments, so forget about this section, at least for now. In the callee's code, additional stack space may be utilized. This is really important, because a lot of times we actually do want to use the stack for a few things, in the called function. So it is perfectly okay as long as the callee cleans it up afterwards. Hey, it's not a problem. At the exit point of the callee, if the callee has a scalar value, return value, we are going to use register A to store the return value. Okay, so this kind of echoes, the contract on the caller side. The register A is used to specify the return value. The callee is responsible to pop the return address, and then the callee would use the popped return address to return to the caller. All right, so do we have any questions about this kind of really short but really concise document that describes the agreement between the caller, the code that is doing the calling or the invoking, and the subroutine that is being called, and I call it the callee in this case. So do we have any questions about that? We good? All right, well, if you're good, then we are going to take a look at a funny program, and then we'll go ahead and try to implement that program in TTP ASM. And that program is already written. I wrote this program in the Monday, Wednesday class, so I'm going to keep it so that we can save a little bit of time. It is important for us to save time because we're going to lose next Thursday. Next Thursday is Thanksgiving, and the Monday, Wednesday class is not losing any additional days, but we are. So we are losing next Thursday, and as a result, we are going to be one lecture short compared to the Monday, Wednesday class. All right, so looking at this code here, it's a very simple program. Ryan as a subroutine, as a function. So when I say subroutine, it's just me saying function. I know most of you understand the term as function or module, depending on which class you took in CISP300. But in 360, we call those things functions. But I'm kind of more old school. Sometimes I would call those things as subroutines. So just kind of remember that subroutine is the same thing as a function. So Ryan is a function, and the only thing it does is to return a value of 79. And this has to do with Ryan is named after the actress who played a character called Seven of Nine. And it's actually quite interesting. I'm not going to go too much into the detail of the actress, but she actually has some political ties, before her actress career took off. And there were a few kind of interesting things. And then the other subroutine is called Johnny. And once again, I use the word subroutine instead of a function, but they mean exactly the same thing. So Johnny is going to return a value of 5. There's no computation, it just returns a constant of 5. And the reason why this particular subroutine is called Johnny has to do with a movie called Short Circuit, where there's a robot that gained sentience because of a lightning, being struck by lightning. So Johnny 5, that's the name of the robot, gained sentience. So that's why this is named after Johnny. And then we have another subroutine called 84, just spelled out 84. And all it wants to return is the return value of Ryan and added to the return value of Johnny. Because one is 79, the other one is 5, the sum is 84. So that's why this particular subroutine is called 84, which by today's standard sounds like a restaurant. I think we have 400 degrees or something like that, and then there's another one for bakery. I think it's 85 degrees or 85 degrees, somewhere like that. um, and then I think we also have marijuana shops, named after some numbers. I cannot remember. It's like 13 ounce or something like that. All right. So from the perspective of the C program, this is what we're going to do in main. All it wants to do is to call 84, do the typecasting, and then print it out. Now, the typecasting and the printing, I cannot do it in TTP, so we kind of have to use a different way to verify that the program does work. So before I proceed to write this program in TTP ASM, in assembly language, are there any questions about the C version of this code? Okay, really kind of simple stuff, right? Until we try to implement it in assembly language. Because there are a few things that are a little bit tricky, but I think that's kind of the whole point of this class, is to handle all those tricky cases. So what we'll do is I'm going to write new code, because the process of writing the code in assembly language, I don't want to reuse the code from the Monday, Wednesday class, so I'm going to write something new in this case. So we'll just call this return value dot ttp-asm, and I'm going to display both code at the same time, both the C code and the assembly code at the same time. All right, so on the assembly code side, it would be a good habit to start with a no op, because if you want to run this using the tool, using the command line version of Logisim, simulating the processor, the no op is needed, because of a bug in Logisim. And then the first thing we do is we JMPI to main to bypass the definitions of the other subroutines. So we're going to have a subroutine for Ryan, one particular subroutine for Johnny, one particular one for 84, 84, and then finally we have main. So we'll go ahead and kind of write out main first, and we know main has to stop with a halt, because there's no such thing as a return 0 of our main. When you write a regular C program, you have a return 0, because the main subroutine is actually called by a piece of code that you do not normally see. So that's why it does have a place to return to, and then what happens is then the program terminates with whatever code you specify in the main function. The program will terminate with that code, and then in return, bash or some other shell can interpret the exit code of your C program and then do other things accordingly. Okay, so even though you never were taught, okay, why do we return 0? Why don't we return 1 or -1? That code can be utilized by a shell script, to indicate, okay, did this program succeeded or did it fail? 0 actually typically means it has succeeded. So anything that is non-zero means something went wrong, and then the value can be used to indicate what went wrong when this program ran. Okay, so now we're gonna first handle the call to 84. So in the C code, it's just a call to 84, and we're gonna do the same thing over here. So assuming you guys did your not test program, but the ungraded assignment. So what do we do when we are calling a subroutine? So I will go through the explanation here, but then I'll kind of shortcut and not do the explanation in other places of the same program. The first thing we need to do is to push the return address. Well, how do we push the return address? Well, the first thing is we have to define the return address first. And one way to do it, okay? One way to do it. This is not even the best way to do it, but one way to do it is to simply use a label for that purpose. So when the subroutine is all done, after we call 84, there's nothing else to do. We really just want to continue with the halt instruction. So the address of the halt instruction is our return address. After the function is called, that's where we want to go to, is the halt instruction. So now we're going to have return point 1 here to indicate this is our return address. So this becomes just a push of return point 1. And now we have to kind of recall how we do the push. In C code, the way we push is to decrement the stack pointer first, and then followed by storing whatever we want to push into the location that the stack pointer points to. This should be nothing new because we talked about this on Tuesday. Okay, and I gave you guys a ungraded assignment, and in the process of doing that ungraded assignment, this stuff should be reviewed already. So to do this in assembly code, we have a decrement D for decrementing the stack pointer, and then we have an ST instruction to handle the other one. But since we cannot store a label or a compile time determined immediate value to a location pointed to by a register, we first have to use an LDI instruction to put that constant into a register first. So any register other than register D is fine at this point, and then we would copy the content of register A to where the stack pointer, which is register D, is pointing to. Yep.
So right now we've got register D holding the return pointer, right?
Register D is the stack pointer, yes.
Yeah. Okay, so register D is the stack pointer, and then we're giving register A the value that we want to store in our return pointer, and then we are storing the value that is stored in A into B then?
Yep.
Gotcha.
Yep, that's exactly what we're doing. And in TTP, there's no way to get around having to use this extra register, simply because the architecture does not have a way to combine the two operations into one. All right. And then don't forget that at this point we're supposed to call the subroutine, so a JMPI to the subroutine is needed. So in this case, it is calling 84. And now we get to let's deal with Ryan and Johnny first, because those two are super easy to deal with. Each one has to LDIA with the return value, because 79 as an integer is a scalar value. So we just specify 79, we load 79 as a constant into register A, and then we have to do the return code. So the return code I'll just explain it one more time, because that was something that we talked about on Tuesday. So we need to pop the return address into a particular register. Let's call that register B this time. So to do a pop, the first thing we have to do is to do a LD, which is the opposite of a ST, because load is going to the location in RAM pointed to by a register, retrieve the content, and then copy that to some register. It doesn't have to be some other, it can be the same register. It's just that at this point of time, we are not going to see a lot of cases where we need to do loading the content in memory pointed to by a register to exactly the same register. Sometimes we're going to have to do that. All right, so in this case, it would be B, D, like so. And then we have to increment the stack pointer. So that's an increment of D. So to be, just to make it more complete, I'm spelling out, these two operations. The first one is B is whatever the stack pointer points to, and then the second one is the auto increment of the stack pointer. So now that B has the return address, the next thing we want to do is to say, hey, program counter, I want you to have the same content as register B, because register B at this point is the address of where we want to continue execution. The program counter points to the next location to fetch our opcode to execute, and therefore, by changing the program counter, we accomplish altering the path of execution. In this case, where we need to go depends on the return address that was pushed on the stack by the caller. So a JMPB is going to do the trick. We looked that up on Tuesday. JMPB does exactly the same thing as what I described here of copying register B to the program counter. All right, so knowing this is going to get the subroutine Ryan implemented, we're going to go to Johnny, and it's going to be about the same thing, LDI A5, and then the rest can be the same, except this time I can use register C. There's no reason why register C cannot be used. So we have that for Johnny. Okay. So the tricky part is 84. So in 84, the first part is easy, okay? We just have to call Ryan first. So that means we have to specify a return point. So we use a label return point 2 to register, okay, this is where the subroutine needs to return to continue the operation of 84. So the first thing we do is to call Ryan. So by now, I think, I'm hoping this looks kind of boring because it's the same stuff that we talked about earlier. Decrement D, LD, some register. I can use register A at this point, okay? Register A is not doing anything special at this point. So I'm going to do LDI A with return point 2, STDA, and then JMPI to the subroutine, which is Ryan. And at return point 2, we're going to have to call 5, okay? Or we'll call Johnny, which is going to be about the same thing, decrement D, LDIA with return point 3 this time, STDA, and then JMPI to Johnny this time. And then we specify return point 3 here. And then we just do the usual return stuff for any subroutine. So we can do a LD, I'll choose B this time again. Increment the stack pointer, and then do a JMPB. So it looks like this would get the job done, but wait, hold on a second here. Aren't we supposed to be adding the return value of Ryan and the return value of Johnny? That should become our return value for 84. So right now, it's not doing it, right? So the question is, how do we do that? Well, we have a problem. The problem is, at a particular point, at this point here, okay? So I'm just going to stash a no op here just so that I can have a place to comment. So at this point here, register A has the return value of Ryan by the convention that I just mentioned today. Is that okay?
Why would it have the return value of Ryan? Why would it have the return value of Ryan?
Because that's the agreement. The agreement says, if a subroutine has a scalar value to return, it would be returned in register A.
Okay.
And Ryan does have a scalar return value. So that's the new stuff that we talked about today. Yep. So that is cool, not a problem. But then you can also say, by this point, register A has the return value of Johnny. So now the problem is, we are using register A for both, so how can we possibly add the return value of Ryan and the return value of Johnny? Someone is going to say, well, we got a few spare registers. Why don't we just kind of copy that into the spare register and then use it later on? So in other words, some people may suggest, let's do a CPR, okay? And we just CPR into some other register. Both B and C are available at this point. So that will help save it, right? Save return value of Ryan, oops, in register B. Except this is not going to work because of the caller-callee agreement. So which part of the caller-callee agreement would make this not work? Well, not all the time, but occasionally it might work, but sometimes, most of the time it's not going to work. Why not? Which part of the agreement is going to be problematic here? I need to have a way to play the jingle of Jeopardy. Bum, 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 bum. It has to do with the assumption that something that is important to a register, that is important to the caller, once you call a subroutine, the subroutine can trash all the registers. So that means this register B that we say, oh, okay, we're just going to save in register B. You have no telling what registers would be trashed by the subroutine that we are about to call. But then someone's going to point to the definition of Johnny and say, hey, Johnny only uses the register C, so register B is going to be safe. You're not supposed to know that. Okay? So this is a good time to specify, when a program works, it doesn't mean it is right. Okay? In other words, this program, the way I do it now, will work, but it is not right. Because if I change the implementation of Johnny and actually use register B to temporarily save the return address, then it's not going to work anymore. So we need to make sure, so what a right program is, what is a correct implementation, is regardless of the implementation of the subroutine, the caller will continue to work. Is that okay? Because it is by that standard that I will be grading some of the homework assignments. Is that okay? So it's not just whether it quote unquote works in a very specific case. It has to work, in all the cases as long as the caller-callee agreement is honored. Are we good with that? Okay? All right, so if this approach is not going to work, okay, what are we going to do I need a place, okay? I need a place to temporarily save the value of the return value of Ryan, okay? That's what I need to do. But I don't have a place yet, okay? So what should I do? What should I do? Of all the concepts that we have talked about so far, can someone suggest, I think we can use that place. And that place is, it would allocate and deallocate dynamically. RAM. It would be somewhere in RAM. Mm-hmm. That we don't have a heap. We have never talked about the heap in this class, but you're close. The stack, exactly. We can stash it on the stack. So that would be a great idea. So that's what we're going to do here. So now we want to push register A on the stack. Because, hey, the called subroutine is not supposed to mess around with the stack that I own, okay? So this would be a good place to do it. So pushing register A is going to be decrementing the stack pointer, stda. So these two instructions is pushing register A on the stack. So this way I am saving the return value of Ryan temporarily on the stack, so that later on I can pop it back to finish the calculation.
And it means the other gremlins don't mess with it, right?
The other thing cannot mess with it, yes, or at least not supposed to. Just because it's not supposed to doesn't mean that it will not do that. Because in C and C++, you can access an array out of bound, and you can mess around with a lot of stuff that way. But we haven't really talked about arguments or local variables yet, so I can't really illustrate that concept. But so for now, it is safe. All right. So that means by this point, okay, by this no op instruction, I now have the return value of Johnny already in register A because that's the agreement between the caller and the callee is if there is a scalar value to return, it will be stored in register A. Okay, we got that. But at the same time, we also have, okay, so I'm going to just use this notation here. The top of the stack, which is where the stack pointer points to, has the return value of Ryan. Okay, so we have both pieces of information now, okay, which is great. But I cannot do an add operation. I mean, I think most of you would go like, oh, so that means I can just add to register A whatever register is pointing to. Well, we cannot do that. We cannot do this not because of syntactical reason, but because of the limitation of the processor. There is no pathway from the D port of RAM to one of the two inputs of the ALU. There's simply none. Okay, so we cannot do this. As much as it would kind of seem to save some instructions, we can't do that. All right, that kind of sucks. So what we will do is to say, well, we can do something like that. Okay, we can pop the value from the stack into register B first. So that would entail, doing an LD first, followed by increment SP or register D, and then at this point, the return value of Ryan is now in register B. So if I add register B to register A, hey, that turns out to be the sum that I need. This is the return value, and now we can proceed to the rest of this code to finish up the returning to the caller. Yes?
I understand what's going on with the add and the LD. What's the purpose of the increment B again?
That's part of pop. That's what pop is supposed to do.
Oh, right.
Yeah, pop needs to grab whatever the stack pointer points to and put it somewhere else, and then it has to increment the stack pointer. Because the stack grows down as we push more items, but as we pop and remove items, we have to increment the stack pointer so that we, quote unquote, deallocate those locations so they can be reused. All right. So are there any questions about this code before I test run it? Okay, so I got some really exciting news. I added a new feature to the assembler. Yes. And I think some of you will kind of appreciate it because it's actually quite useful. So what we'll do is we are going to submit this code first, okay? And what I can do is to kind of go to two different places. So I can use one to kind of run the program, the other one to maintain the editor. So we have this this is supposed to be River Spider. And here I'm submitting the code that is in the temp folder. It's called return value .ttp-asm.
And for the River Spider, do you have to have the Google Sheet open on a tab?
No,
or does
you
it
do
just
not.
run on its own?
It will work without the Google Sheet open. So once you set up everything, you do need the Google Sheet to look at the analysis tab, so you can't really avoid that part. But the answer is no, you do not need this sheet to be open. All right, so we go to the assembler, and this is the new analysis tab. I added column F and column G, so it would actually show you on which line this PC or this program counter is corresponding to, and what is the source code corresponding to that line of code.
Okay, I do like that a lot.
Yeah, I know. This is really quite useful because I think this will really help people understand what is going on, which instruction is doing what in what context, okay?
So wait, did you just compiled it, or sorry, you ran it in River Spider,
Uh-huh.
and did you I didn't see you like put it into the document. Did you do that or?
RISC did that. Okay, so let's go back to. So when you look at RISC, I intentionally put in some feedback. So the first part is it will submit the source code to the assembler to the source tab of the assembler. So the assembler will do its thing to come up with the RAM code or the RAM file thing. So then it will finish the assembling and it will validate the object code. So that's by checking the first line to see whether it's raw v 2.0. And then if the object code is good, it would download that code back to the PC, and it would run Logisim in CLI mode, command line interface mode, collect the output as a TSV or the tab separated file, and then that TSV is also submitted automatically by RiverSpider all the way back to the spreadsheet in what we would call the trace raw data sheet. So that's also done automatically. And then when that is all done, it just comes back to say that, yep, the trace data is all uploaded. And then the assembler will do the rest to kind of come up with this.
And you said the assembler doesn't have to be open.
That is correct.
So how do you then see it if you run it without the assembler?
You
open it back up and it'll be there?
Yeah. You want to see that? Yep.
Is it using Google Sheets API?
It's actually not using the Google Sheet API. The problem with using the Google Sheet or any Google blah, blah, blah API is the authentication part, because you have to authenticate that you're the right user and blah, 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 okay? So instead of doing that, okay, since you guys are asking, now this part will not be in the final exam, I guarantee you that, okay? But since some of you are asking, so if you go into the app script portion of this particular spreadsheet, there's one special function called do post. So do post turns this Google app script into a miniature web server, so to speak. So there's a particular URL corresponding to this spreadsheet. And so what RiverSpider is doing is it's interacting with this Google app script via a post request as a URL. So now the protocol is up to me to specify. I don't have to play by anybody else's rule. Question?
Yeah, how did it connect to the file? Because we can't edit your file.
That is correct.
So we made our own.
Yes.
And how would it connect to that one? Is that part of the setup process? Or?
It's part of the setup process. So there is okay, I can only show you the name of the function, but I cannot show you the actual part. There's a simple auth function here. It compares the hash value of a test string. So there's a little bit of quote unquote encryption thing going on, and that's why you have to customize your own setup so that it will only work for yours.
Okay.
And this is how I can guarantee that none of you can mess around with my assembler. Yep. So the process, for those of you who are interested, because I think even though it is a little bit of a hassle to set it up, but once it's set up, it's really handy. So the key is, no pun intended. So the key is secret string.txt. So this is the secret that you guys have to set up, and then you have to figure out the hash value, the MD5 hash value, and then you just make that gigantic array and put it on the other side, on the Google Sheet side. So this way it can match up the two. It's not just a plain match, it's matching the MD5 hash of the secret string. Yeah. So it takes a little bit of work to get that part done, but once it's done, it's pretty easy to work with. All right. So this has to do with the infrastructure of getting RiverSpider to work, and I think it's worthwhile, but it's up to each one of you to decide whether you want to do this all by hand or you want to do it by kind of in a much more automated way. All right. So getting back to this, okay, the important part here is Tag. You just wrote a program, okay, you ran it, but how do we know the program did what it's supposed to do? okay? So if I were to be lazy, I would jump to the end and ask, what is the value of A at the very end of running this program? So the last value of A is 54, and it is done by the add AB instruction on line 40, okay? So right after that, A becomes 54. You guys go like, but that doesn't sound like 84 to me. Well, 54 is in hexadecimal, so the 5 is specifying the number of 16s. So 5 times 16 is 80. 80 plus 4 is indeed 84. So the program did work the way it's supposed to. But there are a few other things that we also need to check, because we also need to make sure that the D register or the stack pointer, quote unquote, is balanced, which means if it started off at 0, it should end with 0. I allocate and work with the stack, and I need to make sure that I deallocate everything at the very end of the entire program.
Otherwise, you'll have like something just sitting in the stack,
Yep.
not doing anything forever.
That usually is a very bad sign, you have some leftover stuff on the stack. Because it means the pushing and the popping are not balanced. It's kind of like, if you look at push as open parentheses, then pop is like close parentheses. So you have unmatched open and close parentheses, and that's always not a good thing. All right, so the program did work, okay? It achieved what it is supposed to do. So the rest is, how did it get it done, okay? How do we call? How does it know where to return to? So for instance, if you're interested in knowing how did it return to the right place when everything is done, then you can go to a line where we have a JMP something instruction, and this makes it very easy to find all the JMP instruction, by the way, because the source line is also quoted here. So all you have to do is to do a Control F and look for JMP, and it will find all the JMP. It will also find a JMP I2. So if you want to specify and exclude the JMP I, you can use JMP and then followed by a space. So that would limit to only the JMP instruction. It would exclude the JMP I instructions. All right. So now the question is, well, here's a JMP-C instruction, and if I go all the way back, okay, excuse my scrolling. Okay, if we look at this one here, this is the first time it returned, and the line number is on line 12. And after the JMP instruction, it continued execution on line 26, which is, I think, in main. So the question is, how does it magically know where to return to? So now you have to you can execute the program backwards, because this is a full trace, which means you can trace the program forward. You can also do it in a backward way. It's like, how did we get this magical value into register B so the JMPB instruction is doing what it's supposed to do? Well, you can run the program backwards, okay? Which means you go back and say, okay, how did we get this value into register B? The last time we did something to change register B is here, which is the result of the LD BD instruction. So this depends on what is on the stack. So who put that thing into the stack? So now you have to say, okay, FE has the value of 13 in RAM. So the question is, who stashed that 13 in RAM into, 13 is the value, and then the location is FE. So now you can search for that, and you can find that, okay, this is how 13 as content is put into the location of FE, and it is done by the STDA instruction on line 23. Do you see how I'm executing the program backwards? Yep.
Stupid question. Is the D in parentheses referring to RAM in this case rather than register D?
I specifically use the parentheses as part of the syntax to emphasize that this is dereferencing. So parentheses D is kind of the same thing as asterisk D. We are basically using D as a pointer, and we are not changing register D, we're changing whatever D is pointing to.
Gotcha. And where did you access RAM in this?
You mean reading or writing?
Yeah. Like just connecting to it, I guess. Let's start reading.
Okay, so for reading, it is reflected in column B, And then for updating, it is reflected by column C.
Oh, and does it use the ST to store it in RAM, or?
Yes, the ST is the only instruction that can store in RAM. So if you find an entry in column C, it has to be the result of a store instruction. Reading is a little bit different because there are certain cases where it would misreport a read, because an LDI instruction would actually tell you which register got changed, but it will also give you a location in RAM that is read, but it will be the wrong location, because that has to do with the auto increment of the program counter as a part of the LDI instruction microcode.
Yeah, I missed the LD store and
Yep.
jump. I think lab. Sorry, the LD ST and LDI lab.
Uh-huh.
It's just locked out for me now.
Okay,
So
I can reopen at least for you to kind of read the content. So just remind me to do that after the lecture, and I can reopen it. Okay. So are we doing okay so far? If the question that you have in mind is, what am I supposed to do with this? Well, okay. So understanding is about connecting. Okay, the whole thing about, okay, I understand or I do not understand is whether you're making a connection between the concepts. So there's also a deep understanding of something, which means the connection goes not just by one hop or two hops, it goes like 4 or 5 hops. You make a direct connection to something that is like 4 hops away from the original concept. That's deep understanding. But the bottom line is understanding is connecting. So what you need to do, there are 2 things you can do. The first thing I would do if I were you and I have my computer right now is I'm going to take a snapshot of this spreadsheet. I would just kind of go to File. I know you guys do not see all the options here because you're not the owner, but you can definitely go to Make a Copy. So make a copy to your own Google Drive. So this way you have your own copy of this entire thing. Okay, that can be useful. I'm not going to change this particular program anytime soon, so you don't have to do it now. You can do that during the lab time. Okay, that's fine. And then after that, okay, what you need to make connections between, there are a few things you need to make connections between. The first one is look at the source code here, okay? Look at the source tab, look at column A, and what you want to do is to look at each line, not counting the comments. Look at each line and then think about what is it doing in this entire program, in the context. So I'll pick a random example here, okay? I'm just going to pick a random example of this instruction here. Just say that this is increment D. I understand this is going to add 1 to register D. That is not particularly helpful because that's a very shallow, quote unquote, understanding of the increment D instruction. So you have to go 1 level deeper, which is how does this, I know register D is a stack pointer, so incrementing D has to be doing something with the stack. So now you're making a deeper connection, 1 level deeper, which is basically saying, okay, am I pushing or popping? Because there are only 2 operations that you can do with a stack. You're either pushing, adding something to the stack, or you're popping, which means you're removing something from the stack. So which one is it, okay? Well, turns out this time it is popping, okay? So then the next question is, okay, we are popping something from the stack, but what exactly am I popping from the stack? From the perspective of how does this code map to the C code? So that's 1 level even deeper compared to just explaining that this is a stack operation, because now you're relating the stack operation to how we translated a C program into assembly code. So that has to do with we are popping the return address from the stack. How does that relate to the C code? Well, in the C code, you don't have to specify anything to return to the caller. That's just quote unquote automatic. But in assembly code, you need to do something very explicitly in order to return control to the caller. That is basically what we are trying to do. This is one part of the steps in order to continue execution in the caller. Is that okay? So just pointing at one instruction here, I can name 3 levels of understanding. The first one is what does the opcode the instruction actually do? Okay, we add one to register D. Big deal. Why register D? What is the significance of register D? It's my stack pointer. If it's the stack pointer, we are doing some stack operation. What stack operation are we doing? We are popping an item from the stack and putting it into register B in this case. Okay, so why are we doing that? Because we need to go back to continue execution in the caller. And how does this accomplish that? It's because of the caller-callee agreement. Okay, at the entry point of a subroutine, we assume the return address is where the stack pointer points to. That's why this works. So that is the kind of thing I want you guys to do as you're reading this code. And you can do that by commenting. Okay? It depends on how you like to work on stuff. One thing you can do is just copy the entire column here. You start up your favorite text editor or whatever editor you want to use. I'm just going to pick a really simple one. I'm going to choose mousepad, which is kind of the same thing as, oh, okay, no, there we go. And I just stash it here. And then what I would do is to go to the line, and then I would just kind of add my own comments here to explain to myself what this is. And you might also want to do the surrounding instructions because the increment D doesn't do anything useful by itself. Now, by itself, it has a significance, but these two combined is a pop operation, and then these three instructions combined is how we return from a subroutine, and then you have to explain why it is getting the job done. It's getting the job done because of an agreement between the caller and the called subroutine that the return address is going to be at the location where the stack pointer points to. That's the agreement. Is that okay? If it sounds like a lot of work, it is. It is because it really is a lot of work, because for each hour in the lecture, you're supposed to spend 2 hours of out of lecture time, and that's not even counting the lab, in order to quote unquote study. So I do want to explain how to study. This is how I would study. Okay, now this is a very static analysis of the original code. Okay, so that's one aspect of studying, or one aspect of making the connections. I improved the assembler in terms of the analysis tab so that you can also use this as a tool for studying. So in this case, it is dynamic because this is showing you exactly what is happening when the program executes. So in addition to the static analysis of the source tab, which is basically the description of what the processor is supposed to do, this is exactly what the process did. So I would also use this particular table. One thing you can do potentially is just to copy all the columns, Control C, and open up Excel or whatever favorite spreadsheet program you want to use, paste it, and now you can use the additional column H, G, and so on, and just write your comments. But this time it is about the runtime behavior. And I would focus on something like, hey, how did we go from PC equal to 1, go to PC equals to 2, 3, or if you prefer, you can also say, how do we go from line 2 to line 49? Well, that's a regular jump instruction, no big deal. And then you want to identify the return, because this is the return here. How did we go from line 12, which is in the end of a subroutine, and continue execution at line 26? That's the return, okay? So this is the runtime behavior, and this is the description of what the processor is supposed to do. So I would make the connection between these two as well. So part of the connection is already done for you, because I have column F and column G to reflect what the PC or the program counter is corresponding to in terms of line number and the actual source code. But you still want to be able to kind of go through all of this stuff here and ask, what do we put into this location, or how do we change the stack pointer, And all of these other columns are designed to help you visualize all of that. Do we have any questions about this? And this is where I can say, you're not going to get this kind of visualization of the execution of a program in any other class. I guarantee you that. Because most of the other classes, most of the other CISP310 sections, they only use the x86 processor. So you'll be able to run the program. You can use a debugger. You can say, I want to stop execution over here. But it never gives you a full trace of the entire execution of the program. Is that okay? All right. So I'm going to give you some really depressing news now, as if this part here is not depressing enough. So, yes, that would be a correct response. So I'm looking at these instructions here and look at these 4 lines, but only 3 instructions. And guess what? In the x86 architecture, line 9 all the way to line 12 is combined to a single instruction called return, RET. You go like, okay, but this is not just it, okay? You look at these 4 lines here, or 5 lines. So look at these 5 lines here in the x86 instruction set. This is simply call Ryan, as in CALL space RYAN. They go like, why are we doing this in this class? Because if it is just call and return, would you understand or would you even think about it is a stack operation? Probably not, okay? Even if the instructor, the professor told you explicitly, this is a stack operation, you just go like, yeah, whatever. This is call and this is return, and that's all I need to know. In this class, I break everything down. But there's also a third purpose of why I teach this class the way that I teach. This is RISC, okay? RISC, Reduced Instruction Set Computer, as opposed to the Intel instruction set, which is a CISC, architecture. And I believe I still have that tab open. Maybe not. Okay. No, I do. Okay, there we go. So there's so CISC versus RISC is interesting because in the CISC architecture, you can use fewer instructions to specify the same operations. In the RISC architecture, one single line of a CISC architecture expands to a bunch of instructions in the RISC architecture. So people naturally would think, why do we even bother with RISC? I think I want to use a CISC architecture. Well, there are 2 problems. The first problem is human-based, which is how many addressing modes can you remember? There are 16 addressing modes with the x86 architecture. So there's direct, indirect, immediate, based and indexed, based, indexed, and biased, and blah, 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 blah. Okay, there are 16 of them. I mean, yes, you can specify a lot of cool operation on a single line. The question is, how many of those options can you remember? Okay, that's one problem. Okay, it has to do with the programmer. It's a human issue. The second problem actually is even more interesting. What do you think will happen if all your cell phones are using a CISC architecture instead of a RISC architecture? Now, obviously, the question in some people's mind is, I don't even know that my cell phone is using a RISC architecture. So I'm going to give you the answer. If your cell phones are using a CISC architecture, you would not be getting the battery life that you're currently getting. It might be halved, okay? Maybe looking at 1/3-ish, okay? So you need to charge your phone a whole lot more. It doesn't make sense, Tech. It simply does not make sense, okay? Because in the CISC architecture, we can combine a bunch of instructions. Let me go back to the prop here. And where's my assembler? Right here. Okay. So in a CISC architecture, we're combining a bunch of instructions into one single one. How can it end up being less efficient when it comes to power, when it comes to energy? Well, the problem is in the CISC architecture, you have a lot more transistors in the processor. And the more transistors you have in the processor, the more power it's going to consume, even if many of the transistors are not really doing anything important. So that's the one reason why CISC architecture seems to be more efficient, because one line or one instruction replaces a whole bunch of instructions. The problem is it is not energy efficient. So for the same reason, you prefer to have RISC architecture in your cell phone so that you can extend your battery life, so you only have to charge it like once a day or twice a day instead of every 2 hours. It's also the same reason why data centers would also use RISC architecture. Because you would think, with Google, Facebook, or Meta, and Twitter, they want to use CISC architecture because you can squeeze more performance out of a CISC processor compared to a RISC processor. It makes sense, right? In your head, because, hey, I only need one instruction to do all of this. I only need one instruction to do all of this. So why would I not do that if I want more processing power? As it turns out, the limitation of how much processing power you can pack into an enclosed space has to do with something interesting. Have I ever used the analogy of several gamers in a room?
Yeah.
Yep. Okay. It's because of that. Because the limitation of how much processing power you can pack in a space has to do with how much heat you can extract out of that space. And CISC being less efficient when it comes to energy efficiency means you cannot pack as much processing power into the same space. So that's why there's RISC versus CISC. So with all of these kind of cool things about RISC architecture, so the next question is, why are we still using CISC architecture with all the PCs, including your laptop computers, your Mac, your MacBooks and whatnot? Okay, there are a few reasons. The first one, yes.
MacBooks, I think they're using their new M1 or M2 processor.
Say that again.
I think MacBooks are using the RISC now.
The M1, the
Yes.
M2. Okay, are they Intel based? Are they
No, their own.
their own?
Yeah.
Okay, so the reason why MacBooks used to use Intel processors was because of a feud with IBM. Okay, it's a long story. I'm not going to go into that one. So let's focus on PCs. Okay, why are we still using CISC architecture on PCs? Microsoft. Yeah, go ahead.
Sorry, I thought you were asking.
No, that's okay. Go ahead.
Well, I assumed it was because it was based on previous versions of Windows, wasn't it? So if you had to rebuild it from the ground up, it would be kind of big.
So I'm gonna go to Debian and look for the GIMP package. Okay, just a random package that I'm looking for. Because one thing I want to show you is the number of architectures supported by Debian. So we'll just look at this particular one. It supports the Alpha architecture, which was the top of the line processor from DEC, or Digital Equipment Corporation. AMD bought it, okay, and so there's no DEC anymore. AMD 64, which is the instruction set of most Intel-based processor these days. There's ARM 64, which is the ARM processor used in servers and in data centers. And I think these are other variants of the ARM. Some may be a smaller architecture, with less, a smaller die. i386, which is the predecessor of the AMD 64 architecture. MIPS, if any one of you are transferring or planning to transfer to Berkeley, the MIPS architecture or the MIPS architecture is a Berkeley invention. It's a very interesting RISC architecture that really kind of make it very difficult to hand code in assembly language, but that's not my job. So when you get there, you will know. PPC is PowerPC, so there are two variations of the PowerPC architecture. If you have not heard of the PowerPC architecture, it's one of the kind of really interesting one. It started off as a project, so I'm digressing now. You can definitely skip this part when you're rewatching the video. So the PowerPC architecture is not only a RISC architecture, it's a very interesting architecture designed to be a pretender, or in more technical terms, emulator. Okay, so it is a joint project between IBM and Apple. So at a certain time so Apple at the time was using the Motorola 68,000 family of processors, and then IBM was using the Intel processor. Both companies said, we don't like the processor that we're currently using. We want to do something differently, and we want to kind of pack more processing power and so on. And both companies said, yeah, but we cannot agree on switching to a particular common architecture. And it's also a lot of software development investment to have to switch an architecture, because you have to change your compiler. Once you change the compiler, there are portions of an operating system that can only be written in assembly language. So all of that stuff has to be redeveloped. And then all the applications like Microsoft Word, or whatever app you run on your computer, all of those would need to be recompiled as well. So it's a lot of work unless you streamline the process of being able to retarget your architecture. So both companies said, why don't we make an architecture that can pretend to be the x86 architecture for IBM, and it can also pretend to be the 60,000 architecture for Apple. They go like, sounds like a good idea. So they went ahead and moved on to that project, and it is called the PowerPC architecture. So after the PowerPC architecture was developed, Sony came along and go like, we are looking for a processor for what we now know as the PS2, PlayStation 2. So the PlayStation 2 has 16 PowerPC processor cores, okay? And one of them is serving as a manager to kind of manage the other 15 processors. But nonetheless, it was a very interesting architecture that has 15 general purpose PowerPC core that can do whatever they want, and then the 16th is the one that has to kind of do all the management and stuff like that. The PS2 was actually used by US military to perform certain types of simulation and whatnot, until Sony decided, I think it's a bad idea that you guys can run whatever operating system you want to run on the PS2, and they locked that feature out. And that was a little outrage. You can look it up online, and there were a few, let's just say, fallouts, because of that. But it was interesting. The U.S. military was purchasing PS2s in bulk to basically make their supercomputers, at least at one point in time.
And it's kind of funny to me that Sony would cut out one of their biggest buyers, because if they were buying them in bulk like that.
So back in those times, a lot of companies are very concerned about IP, intellectual property. So Sony did all kinds of funny stuff, like they would put a rootkit on an audio CD, so that if you try to copy this audio CD, Sony would know that you're copying a audio CD, you're making a copy of that. The problem was the rootkit that was embedded into the CD obviously only runs in Windows, but not any other operating system, was so poorly written that the rootkit itself has a whole bunch of security holes. So it opened up the doors for actual hackers to exploit the rootkit that was on the Sony CDs to launch additional really malicious attacks on PCs. Obviously, Sony got some more flack because of that. So anyway, getting back to PowerPC. So the PowerPC architecture was used by Apple and also IBM. And then Apple at the time was trying to move on to the MacBook or the laptop computers. And Apple was telling IBM, it's like, okay, you guys need to change the die and use the smaller transistors so we can get more battery life out of the MacBooks. Sounds reasonable. IBM says, we would rather not do anything. So IBM just basically refused to change the chip to use smaller transistors to basically force Apple out of the whole thing, because IBM did not want to support Apple. That was kind of the whole deal. IBM says, we don't want you guys to be doing anything with the PowerPC, so it refused to make it low power. And then at the same time, the Intel architecture, this is back to the Pentium 3 processor. So Intel is much more generalized because Intel also sell their processor on regular PCs, not just MacBooks. So Intel at the time already had low power Pentium 3 processors, and then Apple just finally gave up on the PowerPC architecture. It's like, okay, I'm throwing my hands up and go like, okay, I'm just going to give up on the PowerPC architecture, and that's when Apple switched from the PowerPC architecture back to the Intel architecture, because Intel already had a low power P3 Pentium 3 processor at the time, and Apple said it's worth the extra trouble to switch to the Intel architecture just so that they can get a low power option for the laptop computers. So long history here, and then now Apple is finally making the plunge into their own processor because the CISC architecture, the Pentium processor, just doesn't have the same kind of power saving feature as their own chip. Is it M1 or M2?
I think it's M2 already.
M2? Is it using the 7 nanometer process or even smaller now? And I want to look at the transistor.
This is 5.
5 nanometer?
Yeah, second result.
Yeah. So that's why, it's also a non-CISC architecture. It's a RISC architecture. That is why, Apple is switching to its own chip. And somebody's going to ask, so what is the deal about your PC? I mean, how come your PC is not switching to the M2, or how come Microsoft is not designing its own chip to maximize your power efficiency? This is my suspicion, okay? I do not have any spies in Microsoft to confirm it one way or another. But my suspicion is the tool chain used by Microsoft is really rigid and brittle. So they don't want to run the risk of retargeting to a different architecture. And as a result, they have to hang on to the x86 architecture, because if they switch architecture, they have to retarget the back end of the compiler, which is no big deal if you're using GCC or G++, because GCC and G++ was designed to have the flexibility. It's like, oh, you want to retarget this compiler to a different processor? Easy peasy. Get a few graduate students from Sac State or UC Davis, job done for cheap, man. And I don't think Microsoft has the same kind of architecture built into their tool chain. So every time they have to switch to a different architecture, it's going to be expensive. Yep.
There actually is an ARM version of Windows. Like that's, as far as I know, it's poorly maintained, but
Yes.
There's an ARM version that runs on RISC.
Yeah.
Probably through emulation, because I remember hearing about. This was a while ago whenever they first brought it out, but I remember hearing about their whole chain being very poorly maintained.
It's poorly architected. It's poorly architected. That would be the word to say, because if you look at Linux and if you look at Unix, they are architected in a certain way so that dependency on the architecture is only like this much. The rest, you just recompile. If you write your code right, the recompile process is, it's going to take a few days to recompile everything, but you start the whole process and you can just walk away. Okay, and that's why in Debian or BSD, they can retarget any architecture they want. There have been cases in universities for graduate school that they are looking into a more theoretical processor architecture to optimize certain things. So it's not even a real processor on the shelf. They could port Linux to run on the theoretical processor faster than they can fab it. Fab means fabricate. So before they actually get the hardware thing to plug into a motherboard to actually make it run, they could emulate the theoretical processor and have Linux running on it first. That kind of tells you, how much work is involved to port Linux, or something like that to a different architecture, because this is all done by graduate students. It's not even like a gigantic, software company like Microsoft. This is like a few graduate students, just hacking away with GCC and G++, just the back end of it, and rewrite portions of the operating system because they're a small portion that has to be written in assembly language. So,
And it's like you can see it when you go look at Windows. It's even more apparent in Windows 11 because if you go into Windows 11, there are at least like 4 or 5 different layers where you can see it's like, oh, it's this thing running on this thing, running on this thing, running on this thing, and that's why it's so like just bad on performance.
I have 2 words to describe that type of artifact: scar tissues. So Microsoft has tried to get into the embedded system market many times, okay, as far as I could remember, because I started with the embedded system stuff back in the 90s, okay, before many of you were born, okay. Um, and Windows, tried many, many times to get into those and support, different architectures. So x86 and the ARM processor, every single time it was a disaster. Okay, they put in a lot of money, they did a lot of marketing in all of these conferences. They occupied a huge, gigantic booth with a lot of display and whatnot. And every single time it was just a flop in the end. And it has to do with their software is not really maintainable. And the funny part that I want to show you is Windows CE. Okay, there we go. So there's a Windows CE edition. Okay, I'm not quite sure what C stands for, but combined with Windows, abbreviated to Win, it's WINCE, WINCE, which is truly appropriate for the actual product. Anyway, it was I think this portion here, this segment of this lecture really kind of explains, why there are 2 different types of architecture and why the trend is going on in the CISC direction. And, the CISC, is going in the RISC direction. The CISC processors is basically, they continue to exist only because of Microsoft. There are basically no other reason why we still have CISC type processors these days. Are we doing okay so far? Are you guys now convinced that, okay, let me go back to show you the source code here. So are you guys now kind of more convinced that doing this instead of just a single return, yeah, there's a reason behind it. Unless you plan to become a Microsoft software engineer, then obviously all of this stuff here is like, nah, we don't have to deal with this. We'll just rely on Microsoft as a gigantic corporation to continue to push the CISC direction. Are we good so far? All right. So that's kind of the end of today's lecture. As I said a little bit earlier, you probably will need to make some kind of allocate some time to get to this source code here, comment it, write about it, and make the connections, the conceptual connections that I just mentioned earlier in this class. This would also be a good time to mention that at this point, the concepts from one lecture would start to serve as the basis of the next lecture in a much more tightly coupled way. So the concepts, no pun intended, also stack up, okay? And they stack up in a very quick way. So that means, after one lecture, even if it's just the Tuesday lecture, you really want to spend the time to fully understand the material before we start the lecture on Thursday. Because, we are just building things on top of each other at a pretty fast pace at this point of the class. And this is going to be the same direction. We'll keep stacking all the way to the end of the semester. So we are not going to get a clean break like, oh, okay, we are done with the adder stuff now, and we're not going to talk about the adder anymore. Okay, we'll keep stacking up concepts, from this point. Because I still have to talk about what arguments are, what local variables are, How do we allocate those things on the stack? How do we access those things? And then what are pointers, okay, in C++? What are structures in C++? How do we access a member of a structure that is pointed to by a pointer? Yes, I can repeat that sentence again because I have done it many times. How do we access a member that is a part of a structure that is pointed to by a pointer? See, I can say it again. But to do that in assembly language code requires a lot of concepts being stacked up and connected. So I'm just giving you a preview so that you can allocate the necessary amount of time for studying and reviewing the content of this class. Because the final exam is going to be brutal if there is not sufficient understanding of the concepts. With sufficient understanding of the concepts, I think the final exam is not going to be that difficult. I can also tell you what it entails. It entails me giving you the source code in C. I'll give you the faulty code in TTPSM, and your job is to spot all the problems in the code and tell me how you're supposed to fix it. So if you understand all the concepts, it's just pattern matching. It's like, this one doesn't look right. This is what you want to do in C. That's not what it's doing in assembly code because you're missing this line here, or you have this additional line, or instead of this, you have something else. So if you understand the concepts, it's a pretty easy thing to do. You don't have to write your own code. You have to debug my code. But if you don't understand the concepts, you look at the C code, you look at the assembly code, it's like, it looks right. It has kind of the same instructions that we talk about in class, but if I switch the order of some, if I change the order of some, if I substitute one instruction with another instruction, some people would not be able to spot that. So that's kind of the how the final exam is going to be structured. All right, so so now we can go back and for the lab of today. So the lab of today is let's see, stack operations. It's not released yet, so I'm gonna have to release it first. It does have a passcode, but let me set this up first. So I'll give you guys up to 12 p.m. Okay, plenty of time. Let students see the correct answers at that time. Okay. So the key is LIFO, L-I-F-O, last in, first out. And I just need to make sure that you get up to 12 p.m. to get this done. Save and publish. And there we go. So you might need to rely on the simulator of the processor today to answer one of the questions. So just kind of be prepared that you might need to run LogicSim today. All right, okay. So are there any other questions before I turn off the recorder? Okay, all right. So I'm gonna turn off the recorder, get things uploaded.